Alright, now that we have talked about sequences and tuples and sets, and also the power set of a set, a very important concept is needed to formalize and formulate, so that we could move on to building even more complex machines, more complex techniques to be able to study the items that we need in this course. So the concepts that I'm going to now explain now is called a Cartesian product or cross product. So from this point on, we use Cartesian product and cross products interchangeably of two sets. So what is a Cartesian product, or what is a cross product of two sets? Suppose that you have two sets A and B, and so each of them will have their own set of, or their own elements, a number of elements. And remember, sets are unordered, so it could be any permutation of these elements. The cross products of these two sets is a set whose elements are effectively an ordered pair, wherein the first element is member of A and the second element is member of B. And here's how I would write that. So I would say that let A and B be sets. Then cross product of A and B, and I write it A times B, is a set of ordered pairs. I call them I, comma, J. So it's a binary sequence. So it's a two-tuple, such that I is a member of A and J is a member of B. And this is how I write the cross product of two sets. So the cross product of two sets is effectively a set itself made of sequences, wherein the first sequence comes from element A, from elements of set A, and the second sequence comes from element of set B. From extension, then we could have cross products of three sets. So if A, B, and C are sets, then cross product of A and B and C will be a three-tuple, I, comma, J, comma, K, where such that I is a member of A, J is a member of B, and K is a member of C. Again, remember, these are sets, these are memberships, and I, J, and K are elements. And the cross products of three elements, three sets, is going to be a set of three tuples. Let's see a couple of examples. So let's A be a set of 1, 2, and let B be a set of X, Y, Z. What is A cross B? Then A cross B will be a set made of tuples I, J, such that I is from A and J is from B. I could even write my little wedge symbol here. So let's first take a look and see how many elements A cross B will have. See, A cross B should be any combinations of I and J's where I comes from A and J comes from B. So for every element in A, we have the number of elements in B. So for every element in A, we have 3 elements in the second part of this tuple. So we have 2 elements in A. For every one of these, we have 3 elements in B. So the A times B, A cross B, should have 6 elements in total, right? Or effectively the equivalent of 2 times 3. Number of elements in A and number of elements in B. So number of A elements and number of B elements. So then A cross B will have 6 elements. So it will have 1 from A and then X, 1 and Y, 1 and Z. And then we go to 2 and X, comma, 2 and Y, comma, 2 and Z. Okay, perfect. 1, 2, 3, 4, 5, 6. We have 6 elements. 2 elements come from A for the first element, and 2 elements come from B. 2 important things. 1, the first element must come from elements from A, right? And the second elements must come from elements from B. And since these guys are sequences or tuples, order matters. So for each of these elements in the cross product of the 2 sets, the first element is from A, the second element is from B. Item number 1. Item number 2. The set of cross products itself is a set, which means that order doesn't matter. If I wanted, I could have got first used element 2 and then X, 2, comma, Y, and 2, comma, Z, and then moved to 1, comma, X, 1, comma, Y, and 1, comma, Z, right? So these 2 sets are equal. Why? Because although the order for inside of each of these tuples matters, the outside order doesn't matter. So the cross product A comma B, 1x, 1y, 1z, 2x, 2y, 2z is the same as 2x, 2y, 2z, and 1x, 1y, 1z. Why? Because for set, order doesn't matter, but for tuples, order matters. Item number 2. Notice that in cross product of A cross B, the first element are numbers that come from A, and the second elements are letters that come from B. This should immediately show you that the cross product of B cross A will be again a set, but in this set, the first element first come from B, so the first element is going to be X, a letter, and then the second element comes from A. See, the first element comes from B, the second element comes from A, right? So X1, X2, Y comma 1, and Y comma 2, and then finally Z comma 1 and Z comma 2. So from this you should notice that the cross product of A and B is not equal to the cross product of B and A. In fact, for 2 sets, or any 2 sets, the cross products of A may not be equal to cross product of B. There may be some sets though that the cross products may be equal. For example, if set A is equal to 1 and 2 and set B is equal to 1 and 2, then the cross products of A and B are equal, but it's not always the case that the cross product of A and B is equal to the cross product of B and A. So cross product is not a symmetric operation, and we'll see that the significance of like symmetry and reflexivity, and so on and so forth, and associativity later on as we go on in this class. Now, if you have the same set that is cross product with itself a number of times, in this case, let's say that's k times, then we would simplify it with notation a raised to the k. So a raised to the k means that it is the cross product of itself with itself, k number of times. So if you look at this, each of the elements, so basically each element in a to the k is going to be a k tuple, right? Is a k tuple because it's the cross products of a k times. So a to the k is equal to the set k tuple of a I, or rather a1, a2, a k, such that a sub I belongs to a for every I. So for all I, a sub I, these guys, belongs to a, and you have got a k tuple in this case, as you see. Now, a simpler way to list the cross product of two sets is with a table. So in this case that I had the a being 1 comma 2 and b being x comma y comma z, if I wanted to show the cross products of a and b, I would basically draw a table. So a cross product with b is going to be a table where I have b elements here and a elements this way. So x, y, z, and 1, 2. This way I can visualize the elements that I have as cross products. We use these kinds of tables to represent functions that we can enumerate when we have arguments of the function coming from 2 or 3 or multiple sets, and this way we will be able to enumerate the functionality of our functions, as I will get to shortly, with a tabular representation. So elements of a come from x, y, and come from 1 and 2 number, and then elements of b, x, y, and z. So you've got 1x, 1y, 1z, and 2x, 2y, 2z, and this way we can formulate our functions and relations, which will be the next topic that we will cover. So now that we have the definitions of set, and definition of sequences, and definition of cross products out of the way, let's talk about the central component of mathematics: functions. A function is an object that sets up an input-output relationship between two entities. A function can take an input and produce an output, and in every function the same output always produces the same function, the same output. But two different inputs may also produce the same output. So these are two important facts to remember about functions. So we say if f is a function whose input value is b, and its output value is or input value is a, and its output value is b, then we would represent that fact with writing f parentheses a equal b. Now these are one-dimensional functions, and you know, if a and b are numbers, then there will be an algebraic function, and so you can draw the function rather a and b, and then algebraically or graphically your function will be represented kind of like this. So a sub I here, and then this would be b sub I. Okay. Functions are also called a mapping, and we can also say that f maps a to b. So in other words, for kind of English way of putting f of a equal b, we say f maps a to b. It's the same thing. For example, if you look at the absolute value, the ABS, so absolute value of x is a function, right? And it basically returns either x or negative x if x is positive or if x is negative. So if you were to draw this function as a function of x, then you would have x and f of x, or absolute value of x, right? And this is 0, and then the function will look something like this. So for positive x values, it returns the x itself, and then for negative x values, it returns negative x, which is negative times negative will return a positive value. So this will be the absolute function. Okay. Now, with a function, we have two sets that determine, or rather this function draws its values from, the set of input and the set of output elements. So the set from which all the possible input values for the function come from is called the domain of the function. So domain is the set from which your function draws its values from. The set of output elements, that all the possible output elements, is called the range of your function. So usually we represent the function f from domain D onto range R with this notation. So f colon D and the right arrow R means that your function f draws its elements from set D and as input, and then produces elements from set R. So all the possible sets of the output elements are represented as range, and the input elements are represented as D, or the domain of your function. For example, the function ABS that we just talked about earlier, it draws its values from domain Z of integers and produces the values from range Z, which is also the set of integers. However, you could also say that this function ABS draws from integers onto the natural numbers union 0. This is also a good representation as well, because effectively the absolute value produces positive numbers as the output, but it takes as input either positive numbers or negative numbers. But it also produces 0 as output, because the absolute value of 0 is also 0. And if we're talking about integers, we could also talk about absolute value in real domain to draw its values from the real numbers onto the range of real numbers. That's also a good representation. If a function uses all the elements from the range, then it's called an onto. that range. So for example, if you define absolute value from domain Z to range Z, it is not an onto function, but this is an onto function. So this guy is onto, because if you define absolute as being from domain of integers onto the natural numbers union 0, it uses all possible values from the range. When it uses all possible values from the range, it's called an onto function. So an onto, if it uses all values from range, it's called on to the range. To define function and describe functions, there are different ways that you could represent them. One way is with a formula. If you do have actually an algebraic formulation to define your functions, you'll be able to define them that way. If you don't have the algebraic formulation for the function, you could and there's any way to enumerate them, you will be able to enumerate them in a tabular format. And in this class, a lot of the times when we deal with functions, since we're talking about finite machines that have a finite number of states, we can actually enumerate them. So we use either transition tables or transition diagrams and graphs to represent the functionality and definition, formal definition of the machines, the computing machines we're talking about. Now, another thing before I go further is that either the range or the domain of a function could be multidimensional, meaning that it could be a cross product or a Cartesian product of sets. Remember, I said the function, the D and the R need to be sets, but I didn't specify if they should be one element sets or sets of one elements. They could be sets of sequences, sets of tuples, which makes these functions to take on inputs from another set, from a set of sets, basically, or sequence of sets. So to give you two examples here, I'm showing, like, for example, a function f whose domain is actually a cross product, meaning that the domain of the function, instead of being one numbers, is actually a tuple. So each input is a 2 tuple. Or equivalently, it's a ordered pair of integers, right? And the output of this function is just a real number. So if you wanted to see this function, how this actually looks like, this function will be basically kind of sort of like it takes its input from a two-dimensional space. So basically, it's going to look something like this. So this is Z, this is another Z, and the range is going to be output. So if you were to draw, for example, this function, and if I had the equation for it, then it would look like a surface kind of like that, for example, maybe something like this, right? So the input from this function comes from Z squared onto R. So the inputs would look things like 1, 2 or -5, 7, and the outputs would be numbers like 1.27 or 3.14 and so forth. A function may have its range to be actually a cross product of sets. So for example, in this case, I have a function, a hypothetical function, who takes as input one number, natural number, and produces a pair, ordered pair of number for each input. So for example, it might take number 1, and let's say it generates things like -3 and 7. So I don't really have a reason for like a way to visualize this, but just to show you that functions actually can have their ranges or domains to be taken from multiple elements. Now, one of the things that I want to talk about is that if you have a function, and let's just not consider this case actually, because that would be very, very confusing. And if you have a function whose range is effectively, or input domain is effectively a cross product, then we call this a k-array function. So a k-array function is a function whose domain is a cross product generating k tuples. So input of a k-array functions are k tuples. When you have a function whose inputs are k tuples, then we call it a k-array function, and we call the input values its arguments. For example, the addition is a binary function. So a plus b is actually add a comma b. So this is a binary function. If the input is actually from just one set, there's no cross product, then we call that a unary function. An absolute value is a unary function. Addition, multiplication, division are all binary functions. If your input takes multiple values in the form of a k-tuple, then we call that function a k-array function. I'll give you a couple of examples of a unary function and a binary function here. So a unary function, this is an example of a unary function. It's from the domain 0, 1, 2, 3 to onto the range 0, 1, 2, 3, 4. So my input is z sub 4, actually z sub 5, and the output is z sub 5 here. Then if I can define the function f of n to be n mod 5, then for every single one of these guys, it will calculate its modulo 5, and the output will be that value. So how one way to represent this, one way is the algebraic equation that I have up there. Another way is to represent it as a table. So this is my value n, comes from the domain 0, 1, 2, 3, 4, and then f of n, which is the result of my function. So 0 mod 5 is 0, 1 mod 5 is 1, 2 mod 5 is 2, 3 mod 5 is 3, 4 mod 5 is 4. Right? So this will be one way to represent this function. To simplify these guys, I can use the definition of z sub m to be the set of all i's, or all n values, such that n belongs to z and n is less than m, greater than 0. Okay, so in this case, if I have the definition of z sub m as this set, then my function f is going to be from z sub 5 onto z sub 5, and this is the representation of my function. On the right, I'm showing you an example of a two-dimensional function. So a two-dimensional function basically takes the input as a cross product of two values, a binary pair, ordered pair, onto z sub 4, and my definition is g of I comma j is equal to I plus j mod 4, right? So z sub 4, again, just to remember this notation here, z sub 4 is going to be equal to the numbers n, such that n belongs to z and n is between less than or equal to n to 0 and greater than or equal to 0 and less than 4. So then in this case, Z sub 4 will be basically 0, 1, set of 0, 1, 2, and 3. Now Z sub 4 times Z sub 4 is going to be a 16 element set. It's going to be 0, 0, 0, 1, 0, 2, 0, 3, and then 1, 0, 1, 1, 1, 2, and 1, 3, then 2, 0, comma, 2, 1, comma, 2, 2, comma, 2, 3, and finally 3, 0, comma, 3, 1, comma, 3, 2, comma, 3, 3. So this is going to be Z sub 4 times Z sub 4. So this is my domain. And then of course my range is going to be Z sub 4, which is 0, 1, 2, and 3. Now to visualize my number, how it actually looks like is that since I have a binary function, I have two values for my domain. So it's a cross product. Remember when I talked to you earlier about cross products of Z sub 4 and Z sub 4. So I've got 0, 1, 2, 3. So now instead of just one dimension, I have actually two dimensions. So 0, 1, 2, 3 and 0, 1, 2, 3. Now it's very important to keep the order of my numbers. So what I'm going to do is that I'm going to assume these to be i's and these to be j's. So my first element is I coming from the rows. The second element is j coming from the columns. So if I were to calculate this, so for 0, comma 0, g sub I and comma j is going to be I plus j mod 4. So this is going to be 0. Then 0, comma 1 is going to be 1, 0, comma 2 is going to be 2, 0, comma 3 is going to be 3, because it's going to be 0 plus 3 mod 4, which is going to be 3. Right? Which is, you calculate 3 divided by 4, what is the remainder of it, right? So that's going to be that. Then 1, comma 0 is going to be 1, 1, comma 1 is going to be 1 plus 1 is 2, so that's going to be 2, 1 plus 2 is going to be 3, 1 plus 3 is going to be 4. 4 mod 4 is going to be 0. So this is going to be basically 1 plus 3 mod 4, which is going to be 0. Then 2, comma 1 is going to be 2 plus 0. That's 2. Mod 4 is 2. 3, 0, and 1. Because then this is going to be 2 plus 3. So this is going to be 2 plus 3. See, I is the first one, right? And then j is the second one. Here. So 2 plus 3 mod 4. So that's going to be 5 mod 4, which is going to be 1. And then 3 comma 0 is 3, 3 comma 1 is 0, then 3 comma 2, and sorry, this is going to be 1, and this is going to be 2, because this is going to be 3 plus 3 mod 4, which is going to be 6 mod 4, which is going to be 2. So we talked about functions being a input-output relationship that take an input and generate an output. The input could come from a set. The set could be a set of tuples, set of k tuples that takes k arguments, and the output would be another set. The elements come from a set. So we have the domain of the set, all the possible input values, range of the set, all the possible output values. There are special functions that are so special that we give them special names. A predicate or a property is a function whose range is set of true or false. So these are effectively functions that take an input, and the input could be a k-array, a set of k tuples, but the output is one of the two possible values, either true or false. These we call them predicates or properties. For example, even is a predicate. So even n is a predicate. So if we define even n basically from the set of natural numbers to the set of true or false, right? Then that predicate would be the truth or falseness of the statement is n even. So for example, even of 3 is false. In contrast, even of 12 is true, right? So those are predicates. A property or predicate whose domain is a k-tuple is called a relation. So relations are special let's do it this way. Properties or predicates are special functions. Right? The functions whose range is true or false. Relations are special predicates. Right? The predicates whose domain is a k-tuple, or domain comes from a cross product. So if you have a function from, let's say, A cross B cross C onto true false, then we call this a relation. Okay, for example, the less than is a predicate because it takes an input and it generates true or false, but it's also a relation. Less than is a relation because it takes A and B, for example, and calculate and returns true or false depending whether A is less than B or A is greater than B. We can use for both functions, binary functions and binary relations. We could basically, so binary relations take two inputs, a ordered pair, and then generate true or false, right? So less than is a binary relation. For these binary relations, we can, or even binary functions, we can use infix notation. So for example, we could for less than function, we could do either less than parentheses A comma B, or equivalently we could do A less than B. These two basically mean the same thing. This is the right hand side is an infix notation, whereas the function format is a prefix notation. But both would basically mean the same thing.